A crate of mass m is at rest on a surface inclined at angle theta, and the coefficients of friction between the crate and the surface are mu k and mu s. So for part A, let's draw the free body diagram. We have the gravitational force going straight down, the normal force perpendicular to the surface, and the frictional force preventing the crate from sliding down, so it is directed up the surface. Part B, we want to derive an inequality statement for theta if the crate is able to slide from rest down the incline. So the first thing we need to do is redraw the free body diagram, broken into components. If you look at the original diagram, you can see that it's better to draw this as the y-axis and this as the x-axis, so that way two of the forces are lined up. So we're going to have the Fn on the tilted y-axis, the FF on the tilted x-axis, and then using some basic geometry, this angle right here is the same as the angle of the ramp. So that will tell you that the vector, the force across from the normal force, is Fg cosine theta, and along the x-axis will be the Fg sine of theta. So to answer part B, to get the inequality statement for theta, if the crate's able to slide from rest down the ramp, to slide down the ramp, the force on this side, that component of gravity, would have to overcome this static frictional force. So we can set up the inequality statement to be Fg sine of theta has to be greater than or equal to the force of static friction. And we can plug the formulas in. So it's going to be mg sine of theta has to be greater than or equal to mu s times Fn, the normal force. And from this second free body diagram, we can see that the forces will be balanced in this direction using Newton's first law. So we can say that, we can just say the net force in the y direction equals 0, which means that the normal force will be equal to Fg cosine theta, and we'll just go ahead and replace the gravitational force with its formula. So we have mg cosine of theta, and we're going to put this back right there. So we now have mg sine of theta has to be greater than or equal to mu s mg cosine of theta. We're trying to get an inequality statement for theta, so we need to ultimately get theta by itself. So first thing we can do is divide both sides by mg, because that will just cause the mg's to cancel out. So that gives you sine of theta is greater than or equal to mu s cosine of theta. Now to get the theta by itself, if I divide both sides by cosine of theta, then the cosine thetas will cancel out on the right side. And if you know the basic rules of trig, the sine of theta divided by the cosine of theta is just a property that's equal to the tangent of theta. So tangent of theta has to be greater than or equal to mu s. Now technically the answer should be enough to just leave it right there, but just to be on the safe side, because it specifically says derive an inequality statement for theta, I'm going to go ahead and solve to get the theta by itself completely. So to get rid of the trig function here, to move that to the other side, you have to make it an inverse tangent. So the true final answer for this is that theta would have to be greater than or equal to the inverse tangent of mu s. And if theta is an angle that is greater than the inverse tangent of whatever that trig function is, then the block will slide down the ramp. Okay, so let's say the angle of the incline is slowly increased from 0 until the crate starts to slide, and as soon as the crate begins to slide, the angle of the incline is immediately stops increasing. So in part C, calculate the maximum angle to which the incline can be raised, at which the crate must begin sliding, subject to the constraint that the coefficients of friction can never be greater than 1. So, what we're going to do for this is, to get the maximum possible angle, we're going to assume, well, basically that means it's going to have the maximum amount of friction. So, we're just going to say that mu s is equal to 1. Now, I know we said that, coefficients of friction can never be greater than 1. So we've always had, like, mu s is just less than 1, but it's just like it's saying mu s is 0.999. Let's just make it 1, just to make it easier to deal with. So that we know in that case that if I take that value of 1 and put it in right there, that means that theta is greater than or equal to the inverse tangent of 1, and the inverse tangent of 1, with your calculator in degree mode, is 45 degrees. That means with the maximum possible friction, the crate will still begin to slide right about 45 degrees. So 45 degrees, we can say, is that maximum possible angle. And that way, once you tilt a ramp beyond 45 degrees, it's going to slide no matter what. There's no amount of friction that can hold the block in place. And the way to think about that is, if you tilt the ramp all the way to 90 degrees, obviously the block's not going to stay in place if you tilt it up to 90 degrees. So at some point, there's just not enough friction to overcome it, no matter how much friction you have. Part D. The crate begins sliding when it reaches the maximum angle determined in Part C. So as it slides down the incline, does the speed of the crate increase, decrease, or remain the same? So once the crate started sliding down the incline, right before it started sliding, this force, that component of gravity, was balanced out with this force, the static frictional force. But the instant it started sliding, this force basically stayed the same, but this force decreased because it went from static friction to kinetic friction. So because this force is now a little bit less than this force, we can say in Part D that the forces are unbalanced, and because the forces are unbalanced, that means it's going to accelerate. So the answer to Part D is that it increases, and just mention the thing about the static friction turning to kinetic friction, causing the unbalancing of those forces. And in Part E, the crate slides 2.2 meters down the incline in a time of 1.6 seconds, so calculate the coefficient of kinetic friction. Now, one thing that people jump to right away in this, without even really thinking about it, is they see a distance, 2.2 meters, and they see a time, 1.6 seconds, so they instantly just want to use the speed formula. Speed is equal to delta x over t, plugging in 2.2 meters over 1.6 seconds. Well, the first thing is that formula doesn't really help to get you anything. And the second thing is it's not even a valid formula, because we just confirmed in Part D that the crate is going to be accelerating down the ramp, not moving at a constant velocity. So it's irrelevant to do something like that. The way we want to solve this is we have to set it up as kinematics, because if the crate's accelerating at a constant rate, if you know the initial velocity of the crate is 0, since it started at rest, and the delta x, the distance it slides, is 2.2, and the time is 1.6, the one variable that connects kinematics with Newton's laws is acceleration, because acceleration shows up in Newton's second law that also shows up in the kinematics equations. So A is the thing we want to look for to help us connect it to the force part of the problem. So we're missing the final velocity, so the formula we want to use is delta x equals VOT plus 1/2 AT squared. Remember the three-step process you go through. First thing is, if there's anything equal to 0, cancel it out of the formula. Since VO is equal to 0, and 0 times anything is still 0, we can just get rid of that whole VOT. So we now have delta x equals 1/2 AT squared, and to get this a by itself, because we're trying to find the acceleration, to get rid of this 1/2, and you could say to divide it by 1/2, but the easiest way is to say just multiply it by 2. So multiplying both sides by 2, we'll get rid of the 1/2, So we have 2 delta x equals at squared. So we're just going to divide by the t squared. So the acceleration is 2 delta x over t squared. And now I can plug in the numbers as the last step. So 2 times 2.2 divided by 1.6 squared, which gives you an acceleration of, we'll just round it to 2 decimal places, 1.72 meters per second squared. We're still not at the final answer yet, though, because that's just the acceleration of the block. And the problem wants to know, what is the coefficient of kinetic friction? So now we have to do the Newton's second law part of the problem. So we'll say that the net force in the x direction, that's the net force going in this direction, is equal to the mass of the block times this acceleration. And the way we do the net force is, that's where we do the positive forces minus the negative forces. So we're going to take the positive forces, which we'll go ahead and plug in the formula. That'll be mg sine theta. So mg sine of theta minus, now we've got to do the negative forces, the ones on this side. So the frictional force, and this is going to be kinetic friction now because the block is moving. So kinetic friction is mu k times Fn, and we know once again that Fn was equal to this right here. So just to do a couple steps at once, we'll subtract mu k mg cosine theta. That's the frictional force. And then we'll leave the right side of the equation just as it is. That's m times a. So notice now that every term in this equation has an m in it. So because every single term has an m, you can cancel them all out. So the acceleration of the block is equal to g sine of theta minus mu k g cosine theta. The g is 10. The theta was 45 degrees back in part C. And the a, we just figured out, was 1.72. So you could just rearrange this equation to get the mu k by itself and plug all the numbers in, and that will give you a final answer. So I want to leave that part for you to do, since that's just pure math from this point on, and see what final answer you get. And just to make sure you've got the correct final answer, the one hint I will tell you is that the final answer is pretty close to what the fraction 3/4 is equal to.